So right in the middle, we're talking about integration, where we're adding up a bunch of stuff and letting the number of terms go to infinity. In that kind of addition, the terms themselves are getting smaller. We end up with an infinite number of terms, but all those terms have been crammed into a finite space. Evaluating an expression f of x dx for all the real numbers between a and b. That's weird because when we think about an addition, we think about a plus b plus c plus d. We think about a countable set with discrete terms. When we're integrating, we're making a sum, but it's a continuous sum, and that is strange. That's the thing that we have to get used to. So now I want to give us some more space. Now we're going to look at sums that are infinite, but differently infinite. Now we're going to be able to write down a1 plus a2 plus a3 plus a4, and just let that go on towards infinity. So we're still studying infinity, but it's different. Now our infinity just goes on forever, and we can see the terms. It's kind of like a discrete infinity versus integration's continuous infinity. And we talked about the three big things: sequences, series, and power series. Let's remind ourselves of what the one-word definitions of each of these things are. A sequence is just a list. S1, S2, S3, and so on forever. A series is a sum, A1 plus A2 plus A3, with an infinite number of terms. You could call any kind of sum a series, a finite series, but that's not the one we're talking about. The interesting stuff happens when we have an infinite number of terms. And a power series is a function. The main reason I call it a function, even though it's not really a function, is that, I guess we can call it a function. I don't know how pedantic I want to be at this moment, but I'm going to call it a function because we plug stuff into it. There's a variable, and it's going to have the form of an infinite degree polynomial. Now that is bad. That is bad terminology. It's a polynomial, it should have a finite degree. And I'm breaking that. But that's how we do things. We start with the starting point. What makes this a power series and what makes this a polynomial? One of them, they look the same. One of them is a polynomial because the terms look like this, but then stop. If the terms just keep on going, we say, oh, this was not a polynomial, this is a power series because these terms go on forever. But we're going to think of it as a function because there's a variable and plug stuff into it. We got to think about what we're going to do with each of these three things. The main thing that we're going to look for is convergence. So we're going to be making decisions. We're going to try to determine whether things converge or diverge. And we're going to start saying diverges as diverges because we're making a distinction between converges and diverges. See, I'm already doing it. Diverges, converges, instead of converges and diverges like a normal human being. Unfortunately for our heroes, we're going to use convergence all across the board, but it's going to mean different things depending on context. Math doesn't do this to us very often. Sometimes it happens. So we're going to talk about convergence of a sequence and convergence of a series. A sequence, that's just a list, converges if the terms have a limit. So a sequence converges if the terms have a limit. That is if the limit as n goes to infinity of Sn exists. That's about convergence of a sequence. This is the simplest kind of convergence. It's just another word we're tacking on to the existence of a limit. So a sequence converges if the terms have a limit. Sequence converges if the terms have a limit. We're also going to talk about convergence when we're talking about series. This is more complicated. Not to state, but to determine. A series converges if the sum is finite. A series converges if the sum is finite. A series converges if the sum is finite. Not converges is diverges. So a sequence converges if the terms have a limit, and so diverges if the terms do not have a limit. A sum converges if the sum is finite, so the sum diverges if the sum is infinite. We have a different question when we're talking about power series because we can plug values of x into the power series. So for a power series, we're not asking whether something converges or diverges. We're asking where does the power series converge? For what values of x does the power series converge? That's the question when we're dealing with power series. For what values of x does the power series converge? When we substitute a value of x into a power series, we end up with just a series. And then the question becomes, does the series converge or diverge? So when we plug a value of x into a power series, we get a series. It's fine. So we're thinking of these power series as functions. We can plug numbers into them. When we plug a value of x into a power series, we end up with a series. So what values of x do we plug into the power series and get a convergent series? What values of x do we plug into the power series and get a divergent series? So these are the things that we're going to be looking at. the next couple of weeks. Actually, this week and then the week after next. Because next week we're looking at nothing. This is what we're looking at. Raises a question, why would we consider such a thing? The big story here is power series. We really only care about sequences in series so that we can look at power series. So what's the big deal about power series? We can use a power series to represent a function. This will be why we care about power series. We can represent functions with power series. Although this is getting ahead of ourselves, here's going to be one that we need to know. E to the x is 1 plus x squared over 2 plus x to the third over 6 plus x to the fourth over 24. And then just keep following this pattern forever. We can summarize this with our cool sigma notation. Here's why we might care about this. E to the x is a transcendental function. Over here, I have a power series, which has the form of a polynomial, and that's algebraic. So it's one way to kind of help us understand our transcendental functions. That's a super cheap justification for this. At this point, that's almost like no justification at all. A more practical one might be learning that how we can work with this form of e to the x. So if I just change the input for x, so like e squared is going to be 1 plus 2 squared over 2 plus 2 cubed over 6 plus 2 to the fourth over 24, and so on. This is not how we want it to find e squared. We have calculators. If you want to know e squared, we just look it up. It's not really as something as simple as e squared that we would even look up in the time before calculating. You would just know the value of e, and you would probably, if you're using it a lot, if it comes up a lot, probably just know what e squared is. There's certain skills that have kind of gone by the wayside as human civilization advances, I guess is the word. We developed calculators so we wouldn't have to be able to multiply very well. You know what I mean? We still tell kids that they're good at math if they happen to be very fast at multiplication. But if you have I don't care how fast the kid is at multiplication. First of all, if the kid is actually doing multiplication the way you taught them, they're not fast enough at multiplication. If they just look at the multiplication, know what you're talking about, and come up with the answer, that's fast. But if they're just multiplying stuff out in the traditional algorithm, no, they are slow. I don't care how fast they do it, it's slow. If you're going from San Francisco to Los Angeles, I don't care how fast you're driving, you're getting there slow. Because we have these things called aeroplanes. If you're outrunning the police, I don't care how fast your car is, you're not going to outrun the radio. You know what I mean? If the kid's doing the normal algorithm, I don't care how fast you think they are at multiplication. They ain't fast. Furthermore, we like to talk about kids, oh, this kid's good at math. No one has any way of knowing that. Oh, my 7-year-old is good at math. What math are they doing? You know, the usual 7th grade stuff. You can't even make that determination yet. You know what I mean? You have no way of knowing if that kid is good at math. They haven't done any. Welcome to calculus. Y'all still haven't been in a math class. I know these are all in the math department. I know it's math, but all the classes that you've been in so far, you've been in pre-calculus, you were probably in pre-algebra. This all pre-math. People ask, what comes after calculus? Math comes after calculus. Math that you need? No. Math that mathematicians like, but not math that any person in the normal course of their lives needs, right? But we have gained a certain advantage. You know what I don't know how to do? Grow or capture my own food. You know what I kind of don't really need to know how to do? Grow and capture my own food. It's weird that we're okay with some skills going by the wayside. And some people are like, oh, kids should be able to do math by hand, but why? How many of you drove here today in a car with an internal combustion engine? Who among you can explain to me how that internal combustion engine works? Usually I get one. There might be one. There's like one person that fixes their own car. They don't want to say anything. That's fine. It's cool. I know the phrase is to say, I see you, but if the person is trying not to be seen, you just got to say, I don't see you. You know what I mean? So we're in this really weird place with math. We've always done it with this way because we had to teach people how to do these operations. But do we really? Really hard case to make. I don't even know if I can make it. Obviously, I can't make it. I'm sitting here making not it. Anyway, what are we talking about? Oh, that's right. You might just know what e squared is, or you've lived your life so devoid of calculators, you just remember the value of e to a sufficient number of decimal places and can multiply it really fast just by looking at it because you've trained yourself to do so. It would be insane to ask you to do that right now because, hey Siri, what's e squared? Siri, you don't really understand me, do you? Please no comment. What are we talking about? Oh, yes. But then comes along some useful stuff. Remember this function? What if I just take e and I replace the x with minus x squared? we find this new representation of the function e to the minus x squared, which, as you can see, is just a polynomial if we stop and a power series when we keep going. This function is a little bit interesting because this one comes up when we start talking about techniques of integration as a function that does not have what I call a nice antiderivative. E to the minus x squared does not have a nice antiderivative. That is, it does not have an antiderivative that is a finite combination of elementary functions. So when I talk about a nice antiderivative, I mean the antiderivative can't be written as a finite combination of elementary functions. So if we want to write the antiderivative of e to the minus x squared, we either use an infinite combination or non-elementary functions. And we've seen both now, non-elementary functions. I can just write the integral from 0 to x of e to the minus t squared dt. Not an elementary function, but it's the antiderivative of e to the minus x squared. Or we can represent the antiderivative of e to the minus x squared with an infinite combination of elementary functions. So here's a 9th degree polynomial approximation of e to the minus x squared near x equals 0. This gets worse the farther we are from 0. It gets better the more terms we add. So e to the minus x squared does not have a nice antiderivative. That means we don't have an antiderivative, it's a finite combination of elementary functions. So to write its antiderivative, we either need an infinite combination or a non-elementary function. Any questions? Not A and B not A or not B. Is everybody okay? Is this too much for the week before spring break? This just has to be sitting in the back of your mind during spring break. That's why I need to get it in now. I don't need you actively thinking about it during spring break. I just need the program to be loaded, sitting there in the background. So we're trying to build up to how we can use a power series to represent functions. Now, in this day and age, I even made this point earlier. It seems kind of ridiculous to try to approximate e to the x with this weird power series when we have a machine that will approximate e to the x very quickly to a stupid degree of accuracy. I'm talking about you, iPhone calculator, and your 20 some odd digits of display. That's just excessive. That's how effortless it is. Our phones that we carry around have a calculator that has more digits than we'll ever need, because most people need to the 100. You need to worry about to the nearest 100, then you've got dollars and cents, and everything's fine. So the other thing that we can do is represent functions with a power series where we just have a description of the function. We don't have an actual named function. We just have a description of a function. So rather than describe a function that we already know with a power series, we can also use a power series to fit a description of a function. So if we have a description of a function, we don't know what the function looks like, we could suppose that there is a power series that fits this description and build the power series to fit the description and see if that tells us anything. For example, here's a description of some function y. This description takes the form of a differential equation. Or, as you call it once you get into the differential equations class, diffie-qs. But a differential equation is just a description of a function. There's some function y, so that when you take the second derivative plus 7 times the first derivative plus 12 times the original function, you get 0. That's just describing some function y. If we don't recognize that this is just e to the minus 3x and e to the minus 4x, we could suppose that there is a power series description. We can suppose C0, C1, C2, C3. I'm supposing that the power series description, set power series solution near x equals 0. I don't know what the coefficients C0, C1, C2, I don't know what those are. But I can take this proposed power series solution and just plug it into the equation. If y is C0 plus C1 and so on, then y prime is C1 plus 2C2x plus 3C3x squared. And y double prime is 2C2 plus 6C3x. The next one would be 24C4x squared, and so on. I just plug all this into our differential equation. And so then we just take these three, y prime, and y double prime, substitute them into the differential equation, and solve for C0, C1, C2, and so on. This would be a crazy thing to do by hand, although not that big of a deal here. Good to give us the idea of what's involved. But this is definitely something that we just asked to do. Computer, give me a power series solution to this differential equation. Any questions? For a brief moment there, I was thinking, I should just write that down. And now I'm resisting the urge to do it. Because it's a super algebra problem. Plus, I haven't told you how to solve for C0, C1, and C2. What you do is you equate coefficients. Notice that when you plug y prime, and y double prime into the left side, you'll have a bunch of constants. Your constant will just be C0 plus 7C1 plus 24C2. That's the only constant that you're going to get when you make a combination of these three functions. And over on the right side, this equation is equal to 0. So that means and it needs to be identically 0. So that means all the coefficients of y double prime plus 7y prime plus 12y, all those have to be 0. So C0 plus C1 plus 2C2 equals 0. Oh, sorry, plus 7C1 plus 24C2. The coefficients of x are only in these terms. So, oh, and it also went backwards. So 6C3 plus 14, oh, sorry, skip the x's. 6C3 plus 14C2 plus 24C1, those three have to equal 0 as well. Questions? So then you'll be able to write C2 in terms of C0 and C1. Do the same thing for the squareds, and you'll be able to write C4 in terms of C0 and C1. It's all good fun, but it's algebraic fun. And I've been told that algebraic fun is not a thing. I don't know why that is, but there you go. I think it's because of the way we teach people math. Like the way you teach people music is to put a recorder in the students' hands and have them play hot cross buttons. Incidentally, every school should be doing this, especially if that school wants to improve its students' math ability. They should be doing music. But no one ever questions that, you know? Everybody's like, what did it have to do with the formula? I don't know, why does that have to wear hot cross buns? Are you going to be a professional recorder player? Or are you going to have to learn to analyze poetry? Are you going to be a professional poetry analyzer? It makes us better, I think. But if I imagine a music class, the way we teach math, if we taught music the way we taught math, it'd be like the first day of music class. It'd be like, well, hello, students, welcome to music. Everybody's all excited because everybody likes music. Oh boy, I can't wait to tell all these other music enthusiasts about my particular brand of music enthusiasm. Have you heard of this kind of music? And other people be like, oh no, and then you're gonna go, I'm on, and then off to town you go. Let me show you how cool this music is. But that's not what we do when students show up in math. This is a music class as we teach math. Hello, students. Welcome to music class. I know you're all excited to be here, but being a class, I have to squash that out of you right away. Music is composed in the Western tradition. Actually, they wouldn't point that out. They would just say, this is music, and base it all on 18th century European white men. Like, that's it. This is music. It's like, well, what about everything that's not 18th century white people? Men specifically. We divide the scale into these 12 tones, 8 of which, see, if this is music class, everybody would hate music just like they hate math. If we taught music the way we teach math, I know you still think, no, I will still like music. Boston's debut album is still one of the greatest albums of all. You would stop thinking that because of all the stupid trauma we inflict. Because after I tell you about all this stuff, I would have a quiz. And I was like, all right, everybody, you're going to take a quiz. This is you on your own with nobody else to help you. And if you don't, it's going to go on your permanent record and ruin your life. And it's fine when we're sitting in a room of adults joking about stuff. But if I'm a teacher and you're a kid, like a 7-year-old, I don't know how old are kids when they go to school, doesn't matter. And you're like a 7-year-old, I'm traumatizing you. I'm making you hate music. You know what I mean? But in math, what do? These are numbers. We divide them up into 10 digits, and then we have some stuff in the middle called fractions. I know you can't wait to get to fractions. That'll be your favorite part. And everybody ends up hating it. You know what I mean? And then Matthew is like, well, what can we do? How do we reach these kids? And someone's like, well, make it relevant to their lives. And then to a room full of kids, they say, let's say that we're a farmer building a fence. We've got 100 feet of fencing and we're going to build it on the side of this river. I actually saw that friggin' problem. There's a river and they're going to put 3 sides of a fence right up to the river. I'm like, well, that's not how you should do things. So also, this is a classroom in San Mateo in California. They ain't going to be building fences. And furthermore, they're not going to be building a fence that has to fit these really weird requirements. You know what I mean? It's not an application. That's not an application problem. That's just another trick that we're trying to teach these kids in an effort to engage them. One of my favorites, you need to find editions of books, math books from the 80s. Find an early edition of a book and then an edition of the book that came out in like in like the early 80s, maybe the late 70s. Because the books had to become more culturally diverse. And so they just changed the names. It's my favorite, most cynical thing I've ever seen happen. You look back on old enough books and like if three people are doing something, it's Tom, Dick, and Harry, right? It's Tom, Dick, and Harry. And then forever it's Tom, Dick, and Harry. Or it's three ABC names like Alan, Bob, and Charles. And it's Alan, Bob, and Charles. Then the next problem is Tom, Dick, and Harry. Then we're back. And it's those just, and so in the 80s, it's like, well, you know, maybe we should diversify a little bit. Oh, you mean include math traditions from other cultures? No, 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 no. Let's just change the names. So like the next edition of the book would be Tom, Dick, and Julio. And it's like, oh, look, we are diverse. Look how much we'll appeal. And school says, a quarter of my students are Chinese. So go, okay, we'll change another name. They go, hang on a second. We just, and then the math book's like, oh, well, I don't know what you want us to do. You know what I mean? And then collectively as a culture, we do the same thing. Why can't you just teach my kids the way they taught me? They go, dude, because you suck at math. That's the answer to that one. Anyway, what are we talking about? This was all to avoid plugging these three functions into this differential equation. So sorry about the babbling, but you're welcome to save this algebra for you. Now you get to plug these three functions into this equation and you get to enjoy the algebra parts. All right, that's it for today. I will see you on tomorrow. Everybody have a good day and thank you for playing.